Good afternoon, everyone. Today, the Atom Seminar has the great pleasure of welcoming Dr. Thiago Pinheiro. Thiago completed his PhD at Rice University and his master's degree at the Federal University of Rio de Janeiro. He's currently a postdoctoral research associate in computational chemistry at Oak Ridge National Laboratory, working in the Chemical Separations Group within the Physical Science Directorate. His research focused primarily on molecular level drug design and applications in biophysics and medicine, leveraging insights from statistical mechanics, quantum mechanics, molecular simulations, and statistical data analysis. Most recently, he was honored with the Riki Kobayashi Fellowship and the Ken Kennedy Institute Fellowship. So once again, welcome Dr. Thiago. Thank you so much for accepting our invitation. It's a pleasure to have you here with us. Now, feel free to start your presentation.
So hello everyone, and thank you for the nice introduction. I know most of you may already know me since I was part of this group a few years ago, but I would like to start by introducing myself a little bit better and giving you all a little bit more information about my background. So I am originally from Rio de Janeiro, Brazil, this tiny state here on the map. And in Rio de Janeiro, I got my associate degree in chemistry during my high school. That is called a technician degree in Brazil, but I guess in the United States they call it an associate degree. And then after high school, I moved to the Federal University of Rio de Janeiro, where I got my bachelor's degree in chemical engineering and master's degree in chemical and biochemical process engineering. And I was honored to be part of the Atoms group. And I will now actually use the simple present. I feel that I'm part of the Atoms family still, so thank you all for having me here today. For my master's, I moved to Houston, Texas, to Rice University, where I worked with Professor Walter Chapman, a great honor to work with such a bright person. And I got my PhD in chemical and biomolecular engineering. And then after a one-day vacation, I moved to Tennessee and started my appointment as a postdoctoral research here in Oak Ridge National Laboratory, which is managed by the Department of Energy of the United States. Again, have done lots of things, but today I decided to talk to you about my work during my PhD at Rice University, in which, truthfully, Professor Philip Singer, Walter Chapman, and Dilip Astagiri, and I, and others in the group, we spent many years thinking about ways to combine quantum mechanics, molecular simulation, and statistical mechanics to leverage a better understanding of MRI contrast agents and NMR relaxivity. So if you are like me 5 years ago and you're not familiar with NMR relaxivity, it's not the same as NMR spectroscopy and MRI contrast, don't worry. I'll try to give you a baseline of what I mean by NMR relaxation and MRI. And I'll promise that I'll start very simple, okay? So I'll start very simple. Indeed, I'll start with a water molecule, okay? So water molecule, one oxygen atom, two hydrogen atoms. If we look into this hydrogen, we know that its nuclei has a proton, and this proton has a spin. Okay, I told you that I would be simple, and spin is a complicated concept to grasp. I know spin is this anomalous angular momentum contribution that pop up in quantum mechanics in Dirac's equation. But for the purpose of the talk that I'm going to give today, we can understand this spin by its phenomenological implication, by just understanding that this is a magnetic dipole. Or if you will, you can even think about it simpler. Just think about spin as a tiny magnet. Okay, so in the nuclei of the proton, in the nuclei of the hydrogen, this proton behaves as a tiny magnet. Okay, okay. So here's the catch: our body is basically composed by water, meaning that we have lots of these tiny magnets in our body. So let's imagine the following scenario. Let's start from a situation where a certain part of these water molecules in our body are all aligned. All of these tiny magnets are aligned. Okay. And then we are going to expose them to an external magnetic field B0 that is perpendicular to the original alignment. So in doing so, these tiny magnets, they will align towards this external magnetic field, B naught, and in doing so, they will relax. And that is what we call NMR relaxation on very brief terms, okay? In doing so, there are two characteristic times that we are interested in. First one is called T1, which is the time associated with this relaxation in the longitudinal direction. And the second one is called T2, which is a little bit more complicated, but it's the time associated with the relaxation in the transverse direction. So that's when the spins lose coherence. They lose the phase alignment. Okay, but why am I talking to you about that on a Thursday morning or afternoon? This has a tremendous application in medicine. As it turns out, different water molecules in different tissues in our body, they have different T1s and T2s. So for instance, the water molecules in the muscles in our body, the hydrogen atoms, they have a T1 of about 1,000 milliseconds, while the fat tissue has about 343 milliseconds. This means that if I create a plot and measure T1s and T2s, in this case, I'm just showing T1. If I measure T1 in different parts of my body and create a plot all the way from white being short T1 and black being long T1, this is what I'm gonna see. And this is called magnetic resonance imaging, or MRI, and that is nowadays an indispensable tool in modern medicine. So, I mean, just FYI, this is not an MRI of myself. If you were, you would be seeing a lot more fat, but that's not me. But here's the problem. Sometimes medical doctors want to tell the difference between two neighboring tissues that have very similar T1s. Therefore, they will have basically the same color in the MRI scan, and we cannot tell them apart. So for that, we need to use something called MRI contrast agent. And here I'm showing the example of Gadavist, which is one of the most widely used MRI contrast agents. So the way that this works is the following. So we expose these water molecules in our body to a paramagnetic ion called gadolinium. So gadolinium is 3+ charged. It has 7 unpaired electrons. And because the magnetic moment of the electron is so much greater than the magnetic moment of the proton, in the presence of these unpaired electrons of gadolinium, the water molecule will relax differently. And in doing so, it's going to relax with a shorter T1. Therefore, it will shine more in the MRI scan. So here's what I'm showing, an MRI scan of a brain here before the injection of gadolinium. And after the injection of gadolinium, where the contrast agent concentrates on the tumor cells, we can see that it shortens the T1s of the water molecules in this area, and therefore it makes it shine, and that way we can see the tumor cells in the brain. Now, if you, like me, is not very excited to take a shot of gadolinium upon arriving at a hospital, your intuition is probably right. Gadolinium can be toxic. I would say that most of these second generation contrast agents are relatively safe. But if you are already in a critical situation with kidney problems or nephrologic problems, or if you have to take multiple MRI scans within a certain time frame, you can face some severe complications like bone accumulation of gadolinium, even brain accumulation, bioaccumulation of gadolinium in different tissues, and so on and so forth. The list goes on and on and on. Therefore, we need better alternatives for these gadolinium chelated structures. So gadolinium is chelated here, as I'm showing, to protect our body, but this may not be enough. However, the search for alternatives for these contrast agents has very little molecular guidance. I actually had the opportunity to go to one of the top premier centers in New York, where they are doing research on developing new contrast agents. There's a lot of great work being done. But the search has very little guidance from a molecular or even electronic and quantum guidance. And part of that is because the models that they use to interpret NMR relaxation and MRI are actually overly simplistic. So just to exemplify what is the mainstream model to model NMR relaxation, let me tell you about this BPP or SBM model. So BPP is due to Blumberger, Purcell, and Pound. Actually, two of them won the Nobel Prize in Physics later on. And their model treat NMR relaxivity pairwisely, okay? So let's imagine these two protons, these two hydrogen atoms, and they are assumed to be hard spheres. So they're non-interacting unless upon contact, when the energy goes to infinity. But these two hard spheres are assumed to be undergoing relaxation on the surface of a sphere at a constant distance, okay? And when we do so, we observe that the NMR relaxation autocorrelation function, this g of t, it's a very important quantity for us, it displays a single exponential decay with a certain amplitude gr of 0 and a certain characteristic time tau r, okay? For those of you in the audience familiar with the Bayes theory, this is actually the Bayes theory adapted for magnetic dipoles, okay? Just so you have an idea of what's going on here. This model was heavily inspired by the Bayes theory. So when we take the Fourier transform of a single exponential decay, we get J of R here. This is what we call spectral density function. And from here, and using quantum selection rules, we can calculate those T1s and T2 that I just told you about a couple of slides ago. Okay, that is all great, except that I don't need to convince you that life is not composed by hard spheres at constant distances. And this model is known not to explain the entire world, right? So over the past 70 years, I would say, what people have been doing, instead of using this power of 2 here, which comes analytically from the Fourier transform of an exponential, they do things like fitting an empirical model or empirical parameter to model the experiments and describe them properly. So I'm not here to criticize these approaches. This is all great. It works. It makes science go forward, but it provides us very little physical insight of what's going on a molecular level, right? And I would say, however, that very, very few papers and groups nowadays provide this type of modeling from a molecular level perspective to describe NMR relaxation. But fortunately for me, one of these groups is located at Rice University, and Professor Chapman is also in this call. So since 2017, Professor George Hirasaki, Professor Philip Singer, Professor Walter Chapman, and Dilip Astagiri have been working on calculating NMR relaxation via molecular dynamics. And they've published many papers. I was lucky to be part of at least 5 of them, and more to come, 2 or 3 more to come soon. And they've used their technique to study bulk fluids, highly viscous fluids, fluids under nano-confinement. And when I arrived at Rice in 2021, we started this project to use this technique to study MRI contrast agents. So let me tell you about what I did and how I'm going to present my results. So what I did was basically a multi-scale approach to improve safety and efficacy of MRI contrast agents. So I did a whole bunch of simulations of MRI contrast agents, and I compared them with experiments to try to convince you that these simulations actually make sense. At some point, I stopped the simulations and started looking at this phenomena more from a statistical mechanical perspective. And that's when we developed these molecular eigenmodes to model NMR relaxation. So I'm going to talk about that too. And at the very end, I'll talk very briefly about our molecular quasi-chemical theory to predict chemical stability for this complex, these contrast agents that are chelated structures, okay? So let me start by talking about our simulations. So the way that our simulations work, it might be very counterintuitive, but bear with me. We have basically 2 ansatz. The first one is that the magnetic dipole's energies are much, much smaller than the thermal energies. So I know I'm talking about nuclear magnetic resonance, but in our simulations, we do not have magnetic dipole's energies in the Hamiltonian. And this may sound counterintuitive, but you can actually see that the magnetic dipole energies, it's about like 1,000,000 times smaller than the thermal energies, at least for the frequencies of the magnetic field that we are interested in. Meaning that equilibrium trajectories, or NMR relaxation, is dominated by Brownian motion at equilibrium trajectories. So the way that you can think about that is more that this approach is like a green Kubo way of getting a transport property due to fluctuations at equilibrium, okay? So we start all the way down from quantum mechanics simulations using Psi4. We get charge distribution, polarizability of these atoms, and then we estimate parameters for a semi-classical polarizable model, in this case amoeba, that we later on use in our molecular dynamics simulations. And from them, we can get molecular modes of NMR relaxation, which I'll talk in a minute. So let me give you a little bit more in-depth detail of what's going on here. So starting from these polarizable force fields, we run the equilibrium trajectories. And again, we analyze these dipoles pairwisely. And during the course of the simulation, we keep track of the distance, r over t, r is a function of t, the distance between these two dipoles, and the angle between them with respect to an arbitrary magnetic field B naught. As I told you, B naught does not contribute to the Hamiltonian, but we do put it there to keep track of these angles, right? So by using these trajectories at equilibrium and this information here that we get from simulations, we can exactly get the NMR autocorrelation function g of t by this exact expression here. So this expression is exact, it's not approximated. Our models may be approximated, but the expression is not. So when we do so, we get the g of t from simulations. We can then perform the Fourier transform and get 1 over T1 and 1 over T2 as a function of the frequency of the magnetic field. And that's what we call NMR relaxation dispersion. We are probing different frequencies or different strengths of this magnetic field B naught. Another thing that we can do is to look at this G of T and extract what we call molecular modes of relaxation. So I told you the BPP model and its equivalent called SBM for the case of unlike spins. They assume that this G of T is a single exponential decay. What we observed, however, at least at this level, is that this G of T is more like a multi-exponential decay. So then using a Padilla-Plass approximate approach, we can extract the poles of this G of T and calculate what are the amplitudes and the characteristic times that dictate or that model this G of T. Later on, I will tell you that this expression here that we use, this multi-exponential expression here, that we assumed as a good model, is actually exact for the case of regular diffusion or constant diffusion coefficient in the system. So we've demonstrated that from derivations using statistical mechanics. But for now, just bear with me and trust that this model works well. So here I'm showing a simulation of a water molecule box with one ion of gadolinium in the center. So as I said, gadolinium is a 3+ charged ion, so it's heavily positive. And there are 8 to 9 water molecules that are strongly attached to this gadolinium ion. To these water molecules, we coined the name inner shell. And here I'm just showing a picture of this gadolinium water complex. So again, 8 to 9 water molecules are strongly attached in this inner shell. And here on this plot on the right, I'm showing the NMR autocorrelation function G of t normalized by G of 0 versus time normalized by the average characteristic time. So I'm showing results from simulations from 5 degrees Celsius, 10, 15, 25, and 37 degrees Celsius, 37 being human body temperature. And here I'm showing the SBM model, which again is the BPP equivalent for unlike spins. And this assumes in this log, semi-log plot, a single exponential. That's why it looks like a straight line. So the first thing that we see is that the single exponential decay, the traditional SBM model, is not able to properly capture the physics of NMR relaxation or this NMR autocorrelation function in basically any temperature, not even at human body temperature. And our simulations seem to have a more detailed physics embedded in this G of t. So actually we went ahead and asked the question, so how many exponentials would we need to be able to reproduce the simulation results? And that's what I'm showing here on this plot on the left. So I'm showing the amplitude P of tau normalized by G of 0 versus the characteristic time tau divided by the average tau. And what I'm showing is that for all temperatures, we need at least 3 exponential decays to explain the simulation data. I'm not claiming at this moment that the simulation results are correct. We will see them checked versus experiments in a minute. But the simulations capture at least 3 important exponential decays for the signal. One important thing that we noticed is the following. So in the literature, it's heavily believed that this characteristic time, the single BPP characteristic time, it follows an Arrhenius-like behavior, okay? And what we observed is that the average tau, so the average of these 3 characteristic times weighted by their relative amplitudes. So the average of these characteristic times, it does follow, as you can see in this sphere, this dot symbols, it does follow an Arrhenius-like behavior. However, the individual modes themselves, so mode 1, 2, and 3, it does not follow a trivial Arrhenius-like dependency with temperature. And in fact, later on, I'm not going to touch on that, but later on, we actually derived from statistical mechanics what should be the temperature dependency of these modes. And we have presented that in a paper, if I'm not mistaken, last year. So this is a non-trivial temperature dependency that we observed for these modes. Okay, now I need to convince you that these things actually work. So what I'm showing here is a plot with R1. So R1 is called NMR longitudinal relaxivity rate. This is simply 1 over T1 that I told you about, normalized by the concentration of gadolinium. And this is versus the frequency of the magnetic field, or the proportional to the strength of the magnetic field. And the simulations results are the ones in the continuous line. This area, this shaded area, represents arrow bars. On the left, I'm showing the results at 25 degrees Celsius, and on the right, I'm showing results at 37 degrees Celsius. And the symbols are experimental measurements that we obtained with our collaborators at Hunter College at the City University of New York. They were amazing. They ran these experiments for us, and here are the comparisons. So what I'm showing here in this gray area is the typical range of MRI scans. So if I go to a doctor now, the MRI will be performed in these frequencies between 10 to 300 megahertz. So this is actually the frequencies that we are interested in. And we can see that for both 25 and 37 degrees Celsius, our simulations actually agree very well with experimental measurements. So this is a great validation about validation of our work, actually. However, you must notice that at low frequencies, and even though we don't care about low frequencies, our simulations, they don't match with experiments. This is because an effect called electron spin relaxation that our classical or semi-classical force fields cannot capture. These are complicated quantum effects that we don't see in our force fields. But because we don't see it, and the experiments do see it, so this delta here, because of that, we can actually calculate the difference between our simulations and experiments and estimate what is the contribution of electron spin relaxation to the total relaxation at low frequencies. So we did that. We took advantage of this problem, and we actually isolated this effect, and we compared with experiments with a remarkable agreement. So that was quite reassuring to validate our approach as well. So moving forward, what I did was to simulate, again, water, gadolinium, but now this gadolinium is chelated by a structure called DO3A butyl. This is the gadavist, the widely used contrast agent that I told you about a couple of slides ago. So we ran the simulations. These were long simulations using these polarizable force fields. This was obviously GPU accelerated, but they took a long time to run. And here, what I'm showing are the results on the left. This is the NMR autocorrelation function G of t versus G of 0. This is over time, also normalized by the average time. So again, I'm showing the SBM model, the single exponential decay in the dotted line. Here in red, I'm showing the gadolinium aqua results at 37 degrees Celsius. And in blue, I'm showing the gadavist, contrast agent results. Okay. Well, first of all, we see that the SBM model, again, the single exponential decay, fails to capture all of this curve for the NMR autocorrelation function for both gadolinium aqua and for the gadavist. It actually fails even more for the case of the Gadavist, as we can see here. On this plot on the right, what I'm showing is the same multi-exponential decomposition that I've shown before, but now for the case of Gadavist. So we asked the question, how many exponentials do we need to explain this data? And as we can see here, we need, again, at least 3 exponential decays or 3 modes to explain this g of t that we observe from simulations. And here on this plot here back on the left, this dashed line, this the Laplace inversion, it shows what happens if we use these 3 exponential decays that we isolated to reconstruct the data. And we see that we have a much better agreement when we do so. Okay, so one interesting thing, however, is that even though the red is just gadolinium in water and the blue is gadolinium with a chelated structure in water, we can see that for both cases, they have very similar characteristic times, obviously normalized by the average tau, but they have very similar characteristic times, meaning that similar phenomena are happening at this molecular scale that lead to the NMR relaxation. We don't know yet what these contributions are, but we can tell that in both cases they are quite similar. They have different amplitudes, different contributions, but they have similar characteristic times, meaning that they might be physically the same or very close to be the same. So this is one interesting result we got. But now again, I have to convince you that these things actually work. So again, I'm showing you a comparison with experiments. So here I'm showing again R1, which is 1 over T1 divided by the concentration of gadolinium, versus frequency of the magnetic field. And again, here's the region that we are interested in, the typical MRI range at 37 degrees Celsius. So as we can see, our simulations, the continuous line, agree very well with experimental measurements within the frequencies of interest to MRI for both Gadavist and gadolinium aqua. So this was quite reassuring. It was very interesting to see that our simulations were matching experiments very well. Again, at low frequencies, we do not agree due to this electron spring relaxation, but again, we can leverage that to calculate the contribution, to isolate the contribution of electron spring relaxation to the NMR response at low frequency. We did so and we presented very good agreement with experiments, so that was again quite reassuring. But more than that, what we could do with the simulations that we cannot do on experiments is to look at these structures in solution at human body temperature. So we could see that at 37 degrees Celsius, this gadolinium aqua has either 8 or 9 water molecules around the gadolinium, and they present very beautiful structures. So those are the structures that I'm showing, the very symmetric structures. And interestingly, what we observed is that for the case of gadobutrol or Gadavist, this chelated structure is actually not symmetric. It actually does not have all the chelating groups chelating this ion, because at this temperature, this would add too much strain to this ring, this macrocyclic ring here. So not all the groups chelate the ion, only 7 of the 9 groups that were supposed to be chelating the gadolinium are actually chelating the ion. So obviously that is an observation that might be limited to the model that we are using, but that was an interesting observation that we reported earlier this year when we published this paper. Okay, another thing that we discovered was the following. So it's believed in the literature that the inner shell water molecules, so those water molecules around the ion, right, they are the most important ones to the NMR signal. So everything that is beyond the inner shell contributes very little to the total NMR signal. What we observed, however, is that the R1, the 1 over T1 NMR relaxivity rate for the longitudinal direction, it actually has a pretty big contribution from the water molecules coming from the outer shell as well for the case of Gadavist. So approximately 45% of the signal comes from the waters outside of the inner shell. And obviously, okay, inner shell is important. It's about 55% within this typical MRI range. But still, it's not that the outer shell water molecules are not important. They are important. And we stressed that again in this recent publication saying that the outer shell needs to be modeled properly and accurately because it responds to a big chunk of the NMR signal. And what we are showing here is, again, the NMR modes of relaxation for inner versus outer shell of Gadavis. And as we can see, they're very different. So for the case of inner shell, we have 2 peaks, so 2 exponential decays. And for the outer shell, we have 3 exponential decays. They do not have similar characteristic times. They have very different amplitudes. This tells us that there are very different physical processes, very different physical and NMR relaxation processes going on in the inner shell compared to the outer shell. So this is a difficult problem to model. We don't know what these processes are, but we know that they're different and they need to be treated correctly. So at this point of my research, I thought about these modes a lot. I asked the question, what do they mean? How can I make sense of them? And I don't really know if I answered that question properly, but I will share with you some of my thoughts on that. And for that, I had to abandon a little bit these computational simulations and look into more of a statistical mechanics approach to model NMR relaxation. So what I did was to look into these molecular eigenmodes for NMR relaxation. That's what I'm going to talk next. And the approach is actually very simple. It escalates in complexity very quickly, but it starts very simple. So I start again from this pairwise NMR relaxation assumption, and I was interested in model this r of t, the distance between these 2 dipoles over time, and this theta, the angle between these 2 dipoles with respect to b naught over time. And I know that if I have these functions, I can exactly calculate g of t, the NMR autocorrelation function, using this expression here. So in this expression here, this is the part that I'm interested in. This is called the diffusion propagator, or the green function. There are many names for that in the literature. So if I am able to predict the probability of having certain distance, certain angle between these dipoles, given a certain initial configuration, I can go back to this integral, integrate that out, and get g of t, and then calculate t1s and t2 very accurately. Now, it took us a while to understand how to obtain this diffusion propagator, but we soon realized actually that this diffusion propagator can be obtained by solving the Fokker-Planck equation. And here I'm showing the case of a constant diffusion coefficient. So this d is not a function of time or of position, so we can factor it out of these operators. And when we solve these equations, we will obtain something like this. Okay, I do not expect you to understand these equations. I don't mean to scare anyone here. All I wanted to do is the following. Let's imagine that we can substitute this multi-integral with a summation, right? So all of this area in red, okay, it's a prefactor, I don't know what it is, we can dump into a certain amplitude. And the exponential, okay, it's a function of minus time, minus t, and all of this other d, kt, grad of u, I don't know what it is, let's dump into a certain characteristic time, tau. So this is the multi-exponential assumption that we were using from the very beginning. So for the case of constant diffusion, we can actually show that the NMR relaxation autocorrelation function will be a summation of multiple exponential decays, not only a single one as the BPP and the SBM model predicted. So actually, that was the key insight of this publication that we published last year. There's one more to come soon, is that the dipole-dipole NMR relaxation is governed by these discrete contributions that depend obviously on the nature of the system, the geometry, molecular interactions, which can be described by solving the corresponding Fokker-Planck equation for these dipoles. So if we can solve this expression here, and best of luck with that, this can get very complicated. But in principle, if we can solve this, we can calculate the appropriate g of t, we can calculate t1s and t2 from theory. And I decided to play with that just to see what I get, and I'm gonna share with you some of the results. I find this very exciting. You may not find it very exciting, but I was absolutely amazed by the math involved in solving these problems. So what I'm going to show first is the case for BPP or SBM. So if I take these two dipoles and again go back to the BPP theory, I'm going to assume that these two dipoles are non-interacting, so the grad of U is 0, and they are at a constant distance, as they assumed. If I solved this problem here, I get exactly a single exponential decay, as they predicted. So that is a great sanity check. Later on last year, I released one of these constraints of the model. So again, these dipoles are non-interacting, but now I'm allowing them to diffuse in the radial direction, okay? So I removed the constraint that they are at constant distance. And when doing so, we observe the multi-exponential decay already. And now I'm working on the case where not only I'm releasing this constraint about the distance, but I'm also adding a potential of interaction between the two of them. So this is moving towards a more realistic scenario. So just to share with you a couple of results, when I solved the problem for the case where I released the constraint on the distance, so now there's an inner radius Ri and an outer radius Rf, and this second dipole can diffuse between this Ri and Rf. I do get many characteristic times and many amplitudes. It's actually an infinite sum of them, and they may decay very quickly, but it's technically an infinite sum of them. And here I'm showing results comparing MD simulations of these Lennard-Jones fluids that I simulated versus theoretical predictions. So here I'm showing the reduced characteristic time, tau k, as a function of Ri divided by Rf, so this radii here that I just mentioned. And as we can see, our theoretical results, which are the dashed line, they agree very well with predictions from MD simulations. And in MD, we can actually not calculate modes that are very short. This is because we get very close to the time step, or even the time step is too large to see this relaxation phenomena. So up to the second mode that we can see in our simulations, we have very good agreement. And more than that, in the case where Ri divided by Rf goes to 1, meaning that these two dipoles become at constant distance again, we see that our theoretical results, all of the high order taus, they decay to 0, and only one remains. This is again the BPP limit correctly captured. So in the limit where these two dipoles are at constant distance, we recovered the BPP theory with a single exponential decay. So that was again a very good check of our model. I'm now showing some results very briefly on the numerical solution of these modes in the presence of a potential. So now not only these dipoles can diffuse around each other, but they are interacting. And for the sake of this example, I'm showing a spring potential, so a harmonic potential. And what I'm showing here is 1 over T1 or 1 over T2 at 0 frequency, again, as a function of Ri divided by Rf, with different values of K. So K being the spring constant of the Kr square model of potential that I used. So as you can see, as we increase K, this 1 over T1 and T2, they increase as well. And again, in the limit where Ri divided by Rf goes to 1, we should recover the BPP limit. And again, we exactly recover the BPP case. So that was a great sanity check. Let me just share with you 2 quick slides. I'm almost done. I have a final part, but this should be quick. I find this very interesting. I'm sorry if this is not of interest to you, but what I observed was the following. So in the case where we don't have a potential of interaction, but these two dipoles can relax around each other, when we move from a certain Ri divided by Rf that is less than 0 and go towards, less than 1 and go towards 1. So again, when we move to a case that these dipoles can diffuse to a case where they cannot, they should be fixed as the BPP. We observe that the eigenvalues that we get, they blow up to infinity. So 1 over that goes to 0, but only the first one remains. It does not blow up, and that's the one that explains BPP. However, when we have the case where we have a potential of interaction, a spring constant K, when we move from 0 to infinite K, so again, we are going to now constrain the distance between these two dipoles, but with a potential of interaction that with K going to infinity, These modes, instead of blowing up, they all collapse to the same mode. And that is how we, again, recover the BPP limit, but not by blowing up the higher order modes as before. They now collapse all to the same mode. So that is a different mathematical way that we can recover the limit of the BPP theory with our model. So I think this is fascinating, but I hope you can appreciate that also. Okay, last but not least, I would like to talk about the MQCT, molecular quasi-chemical theory, that we used to understand the chemical stability of these contrast agents, okay? So the idea here is very simple. We have this chelated structure of gadolinium. Gadolinium is toxic. We want it to be chelated, but sometimes it can leave the chelated structure and be free in the body. And we want to exactly calculate what is the constant of equilibrium for this reaction here, because we do not want it to be released in the body. So for the sake of time, I'm not going to talk about the complexation reaction. I'm only going to talk about the free energy of solvation of these ions in water. But the idea that we are using here is actually very similar from the free energies of solvation to the free energies of complexation. So the way that we do that is, again, by starting with a reaction, the metal with waters and a ligand forming the complex. We are interested in this complex constant, this stability constant. And this constant can be calculated with the excess chemical potentials from the chelated structures and the free ion and free chelated structures. So if we derive this, we can see that we can calculate this excess chemical potential exactly through this equation here in the green box. Now, this expression is exact, but the way that we compute these different terms may not be. So that is the problem. So how do we compute these contributions here is the challenge. So the way that we did that was by using quantum simulations and APBS implicit solvent calculations. So we started with gadolinium and N water molecules, and we did a B3LIP and MO6 level of theory simulations, and obviously effective core potentials, because gadolinium has no negligible relativistic effects in this quantum inner core of the electrons. So we did gadolinium with one water molecule, and then with two water molecules and three water molecules, and calculated the probability of having different hydration states for the gadolinium. So we ran optimization and frequency calculations in vacuum, and with that we could calculate the stability constant of this complex in vacuum. So we calculated this other term here, and then we took this vacuum structure and put it on an implicit solvent model. And using adaptive Poisson-Boltzmann calculations, we could calculate this long-range contribution to the excess chemical potential. So by adding them all together, we could compute the excess chemical potential of these different structures. And this is what I'm showing here. So I'm showing the excess chemical potential of gadolinium with different levels of hydration. So 1, 2, 3, all the way up to 9. And we can see that the ones that present the most stable, or the lowest chemical potential, is, or the more negative chemical potential, are the structures with 8 and 9 water molecules, which is exactly what we saw in the simulations, and this is exactly reported in the literature as well. So gadolinium with 8 to 9 water molecules in the inner shell is the most stable. And more than that, we actually could predict the excess chemical potential for gadolinium 3+, the hydration free energy of that, with a very good agreement compared to experiments. The agreement is within less than 2%. So we actually did that for gadolinium and for manganese. So manganese is another paramagnetic species that is being used and looked into for substituting gadolinium as a new generation of contrast agents. It's a little bit less toxic. And again, we did that for manganese with 1, 2, 3, many water molecules. And we observed that the minimum of free energy happens at n equals 6. So manganese is exahydrated, and the excess free energy that we obtained is in great agreement with experiments. So this is quite reassuring. We are now using this for actual chelated structures. It brings a little bit more challenges to the table, but we are very excited to use this approach to address chemical stability. So just to summarize and conclude, in the first part of my talk, I spoke about the simulations and experiments involving contrast agents. I demonstrated excellent agreement with experiments with no adjustable parameters except for the force fields, if you will, that come from quantum. I've demonstrated the non-trivial temperature dependency of these NMR modes. They do not follow Arrhenius-like behavior. I've demonstrated the similarities in the mechanisms of NMR relaxation between gadolinium aqua and the chelated structure. But I also showed, and I think that is a quite remarkable thing to see, the importance of the outer shell effects to the total NMR relaxation response. Not only the inner shell is important, but also the outer shell. In the second part, I described this new theoretical formulation that we did for dipole-dipole NMR relaxation. And I've described this eigenmode description that goes beyond the BPP. So if you're able to solve the Fokker-Planck equation for the system with the proper boundary conditions and initial conditions, you can actually calculate dipole-dipole NMR relaxation exactly. And last but not least, I spoke a little bit about this MQCT approach that is in excellent agreement, not only for these predicted structures, but the hydration-free energies. And it opens a way to study safety of MRI contrast agents in the future. So with that, I would like to, so in the future, yeah, we are looking into the extension of these modes for real systems, as I said. We are moving towards that. We want to look at simulations of other paramagnetic species and also in the presence of osmolytes, electrolytes to mimic a more realistic scenario in the body. We want to investigate properties of polyelectrolytes with these paramagnetic complexes. There's a lot of interest in here. And we also want to calculate, as I said, chemical stability of metal chelated structures using this MQCT approach. So with that, I would like to thank all of our funding sources, the Professor Walter Chapman's group and Professor Steve Greenbaum's group, which received me for 2.5 weeks in New York and allowed me to actually perform some of these measurements that you've seen myself. And with that, I would like to thank you also for your attention, and I'm happy to take any questions.